Okay, so late last night, Cognition just released this crazy paper, which I'm going to talk about in a second, but I do want to give a little bit more context as to why this paper is so insane and why it's so crazy. So about a year ago, Google released this article called The AI Detective, the Needle in a Haystack Test, and How Gemini 1.5 Pro Solves It. And the whole idea with the needle in a haystack test is for agents that use RAG, or LLMs that use RAG. And the idea is if they have a really long piece of media, whether it be a video or audio or a text, the needle in a haystack test basically says, okay, if there's one piece of information in the middle of my 100,000 word prompt, and I can find this piece of information, then this model passes the needle in a haystack test, right? So for example, if I pass all of Harry Potter, right, and there's one scene where Harry Potter is eating oatmeal, right? And I ask the LLM like, hey, what did Harry Potter, have for breakfast on this day? And if it can find that exact line and correctly return that Harry Potter had this oatmeal, then it passes the test. And then here we can see that, 1.5 Pro did really well. On video, audio, and text, it messed up a little bit. But overall, it did very, very well in the needle in a haystack test. At first glance, this seems really great. And it kind of makes sense, right? Like intuitively, it's like if an LLM can get, a piece of information from a really, really long, prompt or text or whatever it is, then it does understand the text. But what happens in reality is most of that text is kind of useless. So even if I gave this LLM a whole Harry Potter series, the only line that actually really matters is Harry eating the oatmeal. And what happens in practice is Gemini or Claude Code or whatever goes in and vectorizes all this information that you give it. Yes, it's really fast, but in practice, it messes up a lot, right? And this needle in a haystack evaluation is really misleading because a lot of the times it just forgets or misunderstands or confuses certain things. And this has been kind of like the status quo for the past year in AI, using kind of RAG and needle in a haystack as kind of like the end all be all of RAG evaluations, which is absolutely terrible, right? It's terrible and it's stupid. And in practice, it doesn't really work. All right, and this brings us to the actual paper. So the paper is introducing SWE-grep and SWE-grep Mini, RL for multi-turn fast context retrieval. TLDR, we trained SWE-grep and SWE-grep Mini, fast agentic models specialized in highly parallel context retrieval. They match the retrieval capabilities of frontier coding models while taking an order of magnitude less time. And this is kind of the crazy part, right? Like it's 10x faster and it's still getting same or in some cases better results than Claude Code or other models. But we'll get to that in a second. And it's available now in Windsurf's fast context subagent and our new SWE-grep demo playground. All right, so modern coding agents face a fundamental trade-off between speed and intelligence. Okay, so down here, context retrieval historically has been done in two ways. So there's the embedding search or RAG, which is what I talked about earlier, where once the upfront work of indexing the code base is done, queries are fast, but the results are inaccurate, and the embeddings can even be counterproductive as it gives a lot of irrelevant information. So this goes back to the needle in the haystack example, where this kind of been the status quo for RAG, right? For doing things very fast and very efficiently. And the second paradigm is agentic search. So the model uses CLI tools to explore a code base, much like how a human would. Both Claude Code and Klein have noted that this works well for them, and up until today, we agreed. While much more flexible, agentic search has its drawbacks, which are it's very slow, and it forces the agent to look at a lot of tokens that kind of have irrelevant information, right? So the alternative to RAG search is agentic search, which historically has been very, very slow, and again, has a lot of the same drawbacks. There's a lot of irrelevant information. All right, this speed and intelligence trade-off seemed inescapable until we trained SWE-grep and SWE-grep Mini, models which match the retrieval capabilities of frontier coding models while taking an order of magnitude less time. These models now power fast context, a subagent that helps you stay in the flow. And here there are some pretty crazy evals, right? Like it's saying SWE-grep and SWE-grep Mini, are performing a lot better than Sonnet and Opus and even GPT-5, right? Almost twice as good as GPT-5, which is kind of ridiculous. And at the same time, it's just absolutely smoking GPT-5 and all of Claude's models here, which is kind of insane. Here it just tells you where to try fast context. We're going to skip over that. So here's the live comparison. So on the left is, the new model that they just released, and on the right is kind of like the status quo. And yeah, it got all the context in less than 8 seconds, or less than 9 seconds, I guess. And on the right, almost 30 seconds, right? And even though this was almost 3 times longer, right? What this is saying is that the output is actually higher quality. Okay, so down here, it just says you can try fast context yourself in our new playground. You can skip over this for now, but if you want to play with it yourself, just follow this link. Okay, so I'm going to skip to down here to the motivation. So there are a few reasons why we think context retrieval is uniquely suited task for a custom sub-agent. So firstly, it conserves context budget and intelligence for the main agent, which makes sense, right? Having a secondary agent to do all the hard work of retrieving the context and getting it very quickly and very efficiently will make the main agent just that much better. Secondly, retrieval is versatile and broadly useful, which is fair. And retrieval is a verifiable task, which again makes sense, right? Here it's saying that they can define an objective ground truth data set, and they can compute clean deterministic reward to do RL. And we see that up here with the F1 score. So there is kind of like, an eventual goal that they're going to try to hit. All right, so what actually makes SWE-grep fast? So there are a couple of things here. So firstly, parallel tool calls and limited serial turns. So yeah, here it's saying that they are running 8 parallel tool calls, including grep, glob search, reads, etc. And it uses each of its 4 turns as efficiently as possible. Secondly, there are fast tool calls. To match the speeds that we want for SWE-grep, the time that a single tool call takes becomes significant. Then they just optimize these we optimize how these tool calls run through indexing, multi-threading, and restricting the tool set, and co-design the SWE-grep models with this custom set of tool calls. And lastly, fast inference. I'm sure that most of the work probably came in here. Yeah, so this is just, they made their own custom SWE-grep models, which, makes it literally 20 times or 4.5 times faster than Haiku. Which is pretty ridiculous. And here, the way they actually train these models is through RL training. So most coding agents take so long to fetch context because they only issue one or a few tool calls at a time. Each turn of tool calls incurs an additional prefill, an extra network round trip, and decoding overhead. To explore code bases as efficiently as possible, search subagents should be doing many tool calls in parallel, which again makes sense. So here is just, kind of a comparison. So most models only do 1 or 2 tool calls at a time. Claude is doing between 1 to maybe 5 or 6. And then SWE-grep, so the lower bound, which is interesting. So it forces it to use a minimum of approximately 6, and an upper bound of 8. And I think this kind of clues us into why it's just so much faster, because it's forcing the agent to use 4 or more tool calls at a time. So here it just talks more about parallelism. And then here they trained SWE-grep directly with multi-turn reinforcement learning. Then they distilled the SWE-grep into SWE-grep mini and perform additional reinforcement learning to boost the model's performance on the task. And our reward function is an average of weighted F1 scores over file retrieval and line retrieval tasks with respect to the ground truth data set. And then here's just, a training graph. So I'm going to skip over some of this math for now. I'm going to go down to the data and evals. So to train SWE-grep and evaluate models on context retrieval tasks, we use an internal dataset consisting of real-world repositories, queries, and a labeled ground truth of relevant files and line ranges, drawn from our hardest bug reports and internal tests. Interesting. We call this the cognition code search evaluation. So yeah, here they use a weighted F1 score, and this is their comparison against other top models. So here they're just performing a little bit better. I do wonder if this is a result of the models kind of being used to seeing the data specifically for the cognition, code search evaluation. And maybe there is some level of overfitting here. And maybe this, F1 score could be a little misleading. But I do wonder how well SWE-grep and SWE-grep mini will perform in the real world outside of their hardest bug report data set. And then here, just saying that, even though they have better performance, it's just way faster. Yeah, and I'm just going to skip over this as well. So here is why this paper is so important. So fast context as the first step to fast agents. The fast context subagent in Windsurf is our first stepping stone in our roadmap to fast agents. The SWE-grep models will be deployed in DeepWiki, Devin, Windsurf Tab, and future products as we validate and tune for future use cases. End-to-end latency is a moderately non-consensus dimension of research for agent labs. In a world where coding agents grab headlines for having 2 to 30 hours of autonomy, the marketing incentive is to make agents slower, not faster. But we think the pendulum will swing the other way soon, simply because we have the unfair advantage of seeing actual user behavior across sync and async code agents. Here's where I kind of disagree. I think they're just kind of saying, the marketing incentive is to make agents slower, not faster. I think they're just kind of, making up bullshit here. The reality is these companies that are using kind of like agents kind of like offhand, right? The number one bottleneck is inference speed, right? I honestly haven't seen a lot of headlines of, coding agents coding for 20 to 30 hours, which is why I think they're just kind of saying this just to, you know, put themselves in a position of like, oh, we're doing this because we're not doing this for marketing incentives. But I think, I know, and I'm sure they know that the real incentives is, just making faster agents, right? Kind of a bottleneck for, anything AI is just waiting for the AI to finish. And this paper made context retrieval literally 10 times faster. And this is the reason why I think it's such a big deal. Coding agents, I think, are one thing, right? But as we start to make the transition to agents in the real world, right? And agents eventually outside of coding, just doing shit that, takes a lot more computation, right? The number one limiting factor for a lot of things is inference time. And if cognition kind of continues on this path, and I think this is almost like a GPT 3.5 moment, right, for context retrieval, where this is kind of the first big and really well put together model I've seen that is really putting context as its number one priority. And I think this new paradigm of faster agents is just going to open up a lot more opportunities in the coming years.